Hi guys, let's get right back to it. At the end of the last video I wrote out this theorem about properties of the weak star convergence. If you are in an NLS, X star denoting its dual space, and you have a sequence of bounded linear functionals, then the weak convergence implies the weak star convergence. This I already explained why this is true in the last video, and moreover the weak star limits are unique. Why are they unique? Well, because if Fn goes to an F and weak starly, and Fn also goes to, say, a G weak starly, then for all x in x, the only thing that you have to do is f of x minus g of x. Well, use the triangle inequality, and then you have f of x minus fn of x plus fn of x minus g of x. Yeah, but both these quantities, because of the weak star convergence, as n go to infinity, they go to 0, given that the left-hand side does not depend on 0. And this is true here for all x. You could optimize in the supremum norm, say, in the operator norm, not in the supremum norm, because you're working with linear functionals. You can optimize in the operator norm and then conclude that f has to be equal to g. Right. So this is not hard. Now, what's harder is the statement that if you have a complete normed linear space, aka a Banach space, and a weak starly convergent sequence, then again the sequence is bounded. Right. This will be another application of the principle of uniform boundedness. And here we go. So, if Fn is weak star convergent, then for all x in x, there exists constant c depending on x in general, so that fn of x is bounded by that c. And why is this? Well, because the weak star convergence is a statement about convergence of fnx in the underlying scalar field, right? And there we know our knowledge from real analysis or complex analysis that these sequences that map into the real or complex number field, if they are convergent, then they have to be bounded, and that's precisely what's written here, right? Of course, that bound can depend on the point at which you evaluate, but it's not going to depend on the index, that small n that becomes large, right? So that this is true for all n in n. In turn, now the standard moves in the game for pub. So for every x in x, that just says that the supremum of fnx running through all those n's is finite. Maybe let's move this sort of here in the center. Right, so the family curly f, which is that family of bounded linear functionals in x star, is pointwise bounded. All right. But now remember, principle of uniform boundedness, PUB, requires that you work with bounded linear transformations between two Banach spaces. And that's why in the statement of the result that we're proving right now, you need that the domain space, that X is complete, right? Otherwise you cannot apply the principle of uniform boundedness. I gave an example why it fails. This step here, this is different from that result when we proved a similar statement about weakly convergent sequences, right? Because there you work with elements in the bidual, so those are bounded linear transformations that start from the dual space and go to the scalar field. Yeah, but the dual space of any normed linear space, whether complete or not, is complete, right? So there you don't need this additional assumption, but here, when you're dealing with weak star convergence, you need it, right? So it's pointwise bounded, given that X is complete, 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 given that X is given that X is complete by pub principle of uniform boundedness, we conclude that supremum of all those norms, those operator norms running through all the n's, is finite, and that precisely means so Fn less than or equal to C for all n in M. Right? So weak-Starley convergence sequences are also bounded, which is nice. Good. Now, very much like to that one criterion that we had when discussing weakly convergent sequences, there we had a sort of a tool that can help us in identifying whether a sequence is weakly convergent. We will have now a similar tool here for the weak star convergence, starting with a NLS, with dual space. How can I tell if a given sequence converges weak-Starley? Well, necessary criterion, what we just proved is, well, that sequence should be bounded, but that's not sufficient, and I will tell you what is sufficient. Then Fn converges weak-Starley to bounded linear functional, provided one boundedness there exists, C positive, so that Fn does not exceed that C in norm for all n. And now again, remember, for the weak convergence, it was sufficient to have weak convergence on a dense subset. The same holds true here, but now that is of course a dense subset in my base space, the X, not in the dual space. So there exists a dense subset M in X, so that Fnx goes to f of x for all x in M. Right, so weak star convergence on a dense subset plus boundedness yields weak star convergence on the full thing. All right, so proof almost exactly the same as that other thing. So again, by density, choose arbitrary elements, then you can find sequence that creeps up to it, xm in M, so that xm goes to x as m goes to infinity. This is convergence in the ordinary norm on your normed linear space. For any nm, now comes the epsilon over 3 trickery again. So fn of x minus f of x. It has to be very similar, right? Because in the previous result there you had f of xn, now you have fn of x. So shouldn't be too many surprises here. Then fnx minus fn xm plus fn xm minus fxm, and well, let's take this a little bit further up, like so, plus fxm minus f of x. And now, very much like in that other proof, you continue as follows. Here you do the standard trick again, so x minus xm, same you do here, f xm minus x. Now you have control over these guys here because of that density thing. You don't need to worry about this guy here out front, the norm of fn, because of the condition 1. This is going to be bounded. It's not going to escape you anywhere. And that middle thing, well, there you use the weak star convergence, which is an assumption in condition 2, because this xm here, that is of course an element in M, right? So, and then you have control. Maybe I will not write down the remaining details. They are exactly the same as in the other proof, and they are written out in the lecture notes. It's again the typical epsilon over 3. You divide by the constant and add all the things up, and you end up with an epsilon showing the weak star convergence as desired. All right, so I will not write out these steps again. Okay. Instead, let's prove some more exciting things. And what I said in the last video is, so in real analysis, also complex analysis, the Bolzano-Weierstrass theorem is a very fundamental result. If you have bounded sequences of real or complex numbers, could also be sequences in Rn or Cn, as long as this is finite dimensional, this all generalizes, then these bounded sequences, they have at least one limit point. That is to say, you can select, that's why they're called selection theorems, you can select a convergent subsequence. Right? So here's a typical example is if you look at the sequence -1 to the n, so that thing that jumps around +1, -1, +1, -1, it has actually two limit points, right? And it's clearly a bounded sequence. Now here we will generalize this to infinite dimensional spaces, so these theorems, they are much more impressive and they're harder to prove. The ordinary Bolzano-Weierstrass theorem you can prove through an application of the Cantor, that Cantor intersection theorem that we discussed at the beginning of the section on bare category theorem, because you can use this divide and conquer strategy to prove Bolzano-Weierstrass. Now here we will rely on Bolzano-Weierstrass, but on more. Right? So the first theorem that we will prove, this is one of many Helly's theorem. So Helly was one of the absolutely outstanding founding fathers of functional analysis, although he never in his lifetime received the credit that he should have. He was the first one who proved Hahn-Banach theorem, like many years before Hahn and Banach did it, but he did it in a special case. He worked with continuous functions, and so his I mean, we proved this on arbitrary vector spaces, and he proved it in one instance, but he was the first one, and it doesn't carry his name. But this theorem carries his name. There's many Helly selection theorems. This is one of them. So let's formulate it. Let X be a separable NLS, so it has a countable dense subset. Then every bounded sequence Fn has a weak Starley convergent subsequence. Helly, by the way, he was he's not British or American, he was Austrian, and he fought for the Austrian Empire in the First World War, and then became a prisoner of war of the Russians. And actually, while being prisoner of war, he discovered that theorem. So anyway, so now let's do this. So let M be a countable dense subset. That thing exists because we're working in a separable space. Be a countable dense subset of capital X, and Fn a bounded sequence of linear functionals. Okay, an arbitrary bounded sequence. Okay. In turn, if you look at the image sequence for any element in the vector space Fn of x, this will be now a sequence of either real or complex numbers depending on your underlying field, but it is bounded. Right? Standard norm estimate of Fn of x. Fn of x in the absolute value complex modulus is at most norm of Fn times norm of x. That norm of x is clearly bounded for a fixed x, and the norm of Fn is bounded by assumption of the theorem. Okay. is bounded for every x in x. All right. So, in particular, this guy here, Fn, evaluated on the first one in your countable dense subset, is bounded. Yeah, but since our scalar field is either real or complex number field, we use ordinary Bolzano-Weierstrass. Thus, by, maybe I will just say BW, Bolzano-Weierstrass, otherwise such a long name, there exists a subsequence. Yeah, so now the double index notation necessarily has to start. So N1K, K1 infinity, so this is a subsequence of the original Fn sequence. So it is a sequence of continuous linear functionals, and it is chosen in such a way that Fn1k evaluated on x1 converges to some f infinity x1 as k goes to infinity. Okay, this is a consequence of the ordinary Bolzano-Weierstrass theorem, because you're dealing here with these image sequences, which are sequences in either the real or complex number field, and they're bounded. Okay, good. Now you iterate this procedure. Now consider the bounded sequence, well, Fn1k evaluated on x2. So why is it bounded? Yeah, because that guy here that I selected out of this one is a subsequence of a sequence of bounded linear functionals, right? So certainly if I evaluate it on a point, then namely x2, which is the second member of this countable dense subset, that's still going to be a bounded sequence of scalars, right? So, oops, in blue, k from 1 infinity. Good. Now, again, using Bolzano-Weierstrass, because this is a bounded sequence that sub n1k valued on x2, we can find a further subsequence. By BZ, we can a subsequence f now sub n2k. Again, k is the running index. That is a subsequence of f sub n1, n1, not nk, n1, k from 1 infinity, for which fn2k evaluated on x2 goes to f infinity, say x2, as k goes to infinity. All right. Now you probably understand what I'm doing. So continuing in this fashion, inductively, we can find successive subsequences fn sub I k k1 infinity. So these are sequences of continuous linear functionals, so that the following two properties hold true. So the next one, f sub n I plus 1k, k is the running index, is a subsequence of the previous one, f sub n I k, k1 infinity, for any natural number I, and the f sub nik xj converges to f infinity xj, but now for which j? Sk tends to infinity for all, I claim j from 1, 2, only up to the I. And why is this? Well, let me draw a picture here, or rather a table. Let's move this up. So what we are doing here is the following thing. We have on the top level, yeah, yellow is probably good. So on the top level we have our starting sequence, that f sub n, right? So you got f1, f2, f3, so on and so forth. Now in the first instance, you use ordinary Bolzano-Weierstrass, and you select your first subsequence, which is fn1, 1, fn1, 2, fn1, 3, so on and so forth, right? So that second line is a subsequence of the first line, and moreover the second line, when you evaluate it on x1, it will give you that limit, right? Now this is the 0th iteration, and the second line is the first iteration. Now in the second iteration, what you do is you do fn2, 1, fn2, 2, so on and so forth, this being a subsequence of the second line, hence in particular subsequence of the first line. Now how do you do it? Well, you say it converges at x2, yeah, but since it is a subsequence of the previous line, it not only converges at x2, it also converges at x1, because if the one layer up converges at x1, then all the subsequences that come out of it also have to converge at x1, right? So this converges also at x1 and at x2. And that's precisely what's written here. So in the ith line, if you build that tower further down, I can't here because I run out of space, at each row you will have, well, that the first I values, when you evaluate here, you will have convergence, right? So, but now what you need is, you need of course a sequence which, subsequence which converges not only at the first I, but at all these guys, right? Because that's what you want. Yeah, how do you select this? Yeah, well, now that's the diagonal trick. So you go along the diagonal, right? So you go further down here, you build a sequence. Frankly, you don't take the first one, that's wrong. You start from the second one and then go down, right? So now as you go down here this way, so the first entry, obviously by construction now, all the entries here along the diagonal, they will converge at x1, right? This x1 is contained in each line. How about x2? Well, apparently x2 is not contained in the first line, but so what? As k goes to infinity, this is a limit that you care about, of course it will also converge at x2, and it will also converge at x3, because it doesn't matter what the sequence does at finitely many of its first elements, right? Only the limit matters. Okay, so let's write this down in words. To get a subsequence that converges at each xj, so at all these members in the countable dense subset, we consider the diagonal, that's what I shaded in green there, the diagonal sequence, and just look at the picture, that is f sub nk evaluated at k, k1 infinity, this is a sequence of continuous linear functionals, and by construction I have f sub nk k xj goes to f infinity xj. Now for all j, not just up to the sort of k, but for all j up to the capital N. For all j from 1 up to the capital N. Right? So you can apply the theorem that we proved right before this Helly's selection theorem. The theorem right before was saying that you have weak star convergence if you have a sequence of bounded linear functionals. That's what we have here by assumption. And if you have the weak star convergence on a dense subset, right? And that's precisely what we showed here, because the xj's, their collection all the way up to n, they are a dense subset, right? Because our space is separable. And hence you have indeed existence of weak star convergence subsequence or weakly star convergence subsequence, right? So the previous theorem yields the weak star convergence of that subsequence Fn kk k1 infinity, which is the subsequence of our initial bounded sequence Fn, right? This completes our proof. All right. So if you have a separable normed linear space, doesn't have to be complete, then every bounded sequence of continuous linear functionals has a weakly star convergent subsequence, which is a Bolzano Weierstrass type theorem. However, the one that we are probably expecting is actually this one, but there we need bigger guns. So we need to be in a Banach space and we have to be in a reflexive Banach space. This theorem really sort of gets to the gist why reflexive Banach spaces are mighty useful. So then every bounded sequence xn in X has a weakly, you can't do better. In chapter 4 we will have counterexample. We will construct explicitly, actually in a Hilbert space, a bounded sequence that has no convergent subsequence, right? But that theorem says here you have at least one weakly convergent subsequence. So you have to go to that weak notion of convergence, right? And this is really a Bolzano-Weierstrass theorem. I will prove it in the next video, and then we will be done with this section and move on to chapter 4. I'll see you soon.